In this second lecture, we will go into more depth regarding the optimization of a single neuron classifier to try and understand the principles underpinning the backpropagation algorithm. Let's start by reviewing the example of our single neuron logistic regression model. The goal is to learn a weights vector W which, when the data points are projected onto it, will maximally separate the classes. In this example, we have data points X with features x1 and x2. These are linearly transformed by weights coefficients W1 and W2 with a bias term added. Thus you should be able to see that W is perpendicular to the separating hyperplane. This is given by the centre of the projection at the point at which Z here is 0. We can then apply sigmoid activation function F to calculate the prediction probability of each class, where Z greater than 0 will return class 1 and Z less than 0 will return class 0. Now, a common trick which we will use going forward is to then merge the bias term into the linear transform by extending X with a row of 1s. Then the transformation matrix W, actually a row vector in the single neuron case, will encode the bias term as its first coefficient. This then lets us estimate Z in one step through matrix multiplication. So now we can define some notation. Don't worry if this is not all clear. The idea is that this slide acts as a point of reference throughout the lecture and the tutorials. Let's start by referencing the number of training samples as NT and the number of test samples as NTE. We have multiple layers even in a single neuron network, and we will index these with J. This starts with the input layer 0. The input layer actually means the input data, so we say the number of neurons in the input layer is equal to the number of features of your input data plus one more for the bias term as shown in the diagram here. For a binary classification or regression network with a single dependent variable, there will always be one output neuron. Between these layers, for the hidden layers, the number of neurons MJ is tunable, like we saw in the TensorFlow playground, so we can add or take away neurons and layers until our network works best. Now for our training data, we call this matrix X, and this will have shape M0 by NT. So the number of columns is equal to the number of examples, and the number of rows is equal to the number of features plus 1 for the bias term. Y references the ground truth labels for the training data. So this will have length NT, 1 for each example. Y hats are the predicted labels. Our weights matrices, which will contain all the coefficients of our linear transformation plus the bias term, are termed WJ for each layer. I'll come back to the generic shape in a later video lecture. As stated, for a single neuron classifier, we'll have a row vector with the total number of coefficients equal to M0, which again is the number of input features plus 1 for the bias. And this allows us to calculate Z as a matrix multiplication WX. And then our activation function, which acts element-wise on Z, will therefore have the same shape as Z. So this is F. Finally, Li here is the loss for one example. So we've defined our variables, and we know that we need to estimate the best W to separate our classes, but how are we going to do this? So we could just try different values of the coefficients of W until we get the best result, where here I'm pseudo-plotting different hyperplanes rather than the approximates of W itself. Regardless, this is very inefficient. A better approach would be to choose an appropriate loss function Li, which has a minima which coincides with the optimal training accuracy. The properties of any suitable loss function must be that it's continuous, in other words, it changes smoothly. There are no values of W for which L suddenly jumps between two values or changes sharply, ensuring that this means that we'll be able to differentiate L with respect to all values of W. We'll do this by calculating the analytic derivative, in other words by using calculus. Remember the gradient of a function is the slope at some location in the feature space. So the rate of change of y with respect to x, for example. We need this gradient to be defined everywhere for our parameter space, so this creates a problem if we're faced with functions that are not defined at any point, change sharply, or asymptotic or discontinuous. For example, the modulus function. So this has an undefined gradient at 0, since the rate of change of x at that point is 0, and so the gradient involves division by 0. Also, this function tends asymptotically to infinity at a, and this one jumps suddenly in y at x0. At the same time, we don't just want a continuous and differentiable function. What we also ideally want is for the function to be convex. In other words, monotonically decreasing as the prediction improves without any local minima. So this is what we want. And here is an example of where we have a local minima. Unfortunately, while this is possible for single neuron classifiers, as networks get more complicated, this is rarely possible in practice, and strategies are required to avoid getting stuck in local minima. And so this is always something to bear in mind when training. So putting this into practice, let's look at model accuracy as a loss function. Accuracy is the total number of correctly predicted answers out of a total, but considering loss on a per example basis, this is clearly not suitable as a loss function because it returns a discrete thresholded value. This makes it discontinuous, a step function, and therefore not differentiable, whilst at the same time being undiscriminative in that it cannot distinguish between slightly wrong and very wrong answers. Another option is mean square error. While this is differentiable and, as you will see, is used for optimization of regression models, it's not suitable as a classification loss as it has a small range, but also more importantly, if you follow this link, you'll see that mean squared error is non-convex for the case where f of z is a sigmoid, which is the case for logistic regression. On the other hand, cross entropy, which is given by this equation, can be guaranteed to be convex for logistic regression, and the penalty when the prediction is wrong tends to infinity. This is because log of 0 tends to infinity. The loss itself can be split into two parts, the loss when y equals 1. In that case, the second part is 0 because it's pre-multiplied with 1 minus y. And the loss when y equals 0, in which case the first term is 0. So of course, so far we've defined the loss for one training example, but we need to consider the aggregated loss over all training examples, which we will call the cost. So JW here is the cost function or mean loss over all examples I. The loss we will be considering is cross entropy, and F here is our activation or prediction function, which for logistic regression is a sigmoid. Note that we've replaced f of z with just f to make it easier to read. Finally, remember z here is the linear mapping of x by w. So how do we go about finding the values of w which minimize j? As previously stated, to minimize our loss, we need to find the value of w for which the gradient is 0. And we reach this from any position in the parameter space by taking steps in the direction of steepest descent at that point. In other words, by taking steps along the negative direction of the gradient of our cost function, so the derivative of j with respect to w, which is defined as the rate with which j is changing with respect to small changes in w. If we define this small change as h, then the gradient can be found in the limit as h tends to 0. So then if we repeatedly take small steps in the direction of the gradient, we can step in a direction of decreasing j, as shown by this update equation, and we can follow the slope of the line down towards the minima of j. However, we don't want to be slowed down by taking a finite distance approach. In other words, brute force calculation of the change in j for minute changes of each of the parameters. Rather, we want to make use of the rules of differentiation to implement analytic derivatives. For example, hopefully you will all recall from doing calculus at school that the derivative of x with respect to the power n is nx to the power n minus 1. Remembering that if n equals 1, then this will return 1, as x to the power of 0 is 1. Other simple examples that you might remember are that the derivative of e to the x is itself, and the derivative of the natural log of x is 1 over x. All these can be derived through brute force limit calculations, but in practice, once known, then the derivatives of more complex functions can be pieced together from these simpler ones. For example, the ones that we will need are for cross entropy, which includes logarithms, and the sigmoid, which includes exponents within the denominator of the quotient. These will be described in more detail later. Further, when calculating the derivatives of neural networks, we are interested in multi-dimensional gradients of loss with respect to several parameters wi, for example w1 and w2 in our simple toy example. For this, we require partial derivatives, indicated by the following symbol, and read as del L by del W1 and del L by del W2. The gradient is then the vector of partial derivatives estimated with respect to all parameters of the model. So now we are equipped with a definition of derivatives for simple functions. So we have almost everything we need to understand backpropagation, with key exception that unfortunately our loss is not a direct function of our parameters, rather it is a function of f, which itself is a function of z, which of course is the actual term which references the parameters. This requires us to utilise the chain rule of calculus, which tells us that if y is a function of u and u is a function of x, then to return the gradient of y with respect to x, we must estimate the derivative of u with respect to x, and the derivative of y with respect to u, and then multiply them together, thereby cancelling the du's to give us dy dx. So for example, let's estimate the gradient of y equal to the square root of 5x minus 2. So we can let u equal 5x minus 2 and then du dx equals 5. And the derivative of the square root of u, which can otherwise be written as u to the half. So this then follows from the power rule as 1/2 times u to the minus 1/2. Thus, chaining all this together gives us 5 over 2 times u to the minus half, or 5 over 2 times 5x minus 2 to the power minus half. So this at first might seem quite daunting, but what we can do to simplify things is visualize the process as a computation graph. For example, let's start with something a little simpler than cross entropy, assuming that our loss is instead a mean square error between y and z, so no nonlinear activation function, so this part of the expression is what you should recognize as z. We can break this up into stages of gradient computation from right to left. So to start with, we need to differentiate L with respect to the expression inside this bracket here. Let's call that A. Then we need to know what the derivative of A is with respect to Z. And we know that Z is the sum of terms in W1 and W2. So what we want to do is track backwards or backpropagate to get the component derivatives, such that in the end we can return our estimations of the gradient of the loss with respect to W1 and W2. So let's first go through a forward computation, a forward pass. So this means plugging in the values that we have for our inputs and the parameters at this iteration. Let's say that x1 equals 2, w1 equals 4, w2 equals 3, x2 equals 1, and y equals 8. Then if we move forward from left to right, then we have u equals 4 times 2 equals 8. V equals 3 times 1 equals 3. Z equals u plus v, therefore it equals 8 plus 3, or 11. A equals y minus z, which equals 8 minus 11, and therefore equals minus 3. And finally, putting it all together, as L equals a half a squared, then it's equal to a half, or 0.5, times minus 3 squared, which is 9, so it equals 4.5. So now let's consider the backwards pass, otherwise known as backpropagation, starting from the right-hand side. So we've just revised the derivative of a power, so we can now say that the derivative of L with respect to a half A is A, since the power of 2 will come down and will cancel with the 2 in the denominator of the fraction. In the next step, we need del A by del Z, which, as we have a minus Z, will return minus 1. So if we multiply this with del L by del A, which we know from step 1 is A, then we get minus A, or minus Y minus Z. In the third step, we take this process one step further, and now we add del Z by del U, which, as Z equals U plus V and the derivative of a variable of unit power is 1 and U is positive, this means that it returns positive 1. So multiplying del L by del Z from step 2 makes no change. Finally, we get all the way back to estimating del L with respect to each of our parameters. So for W1, the derivative of W1x with respect to W1 is x. It's again, W1 is raised to no power, so its derivative is 1. So the combined final result is therefore minus y minus z times x1. So hopefully here you can see the components of the chain rule in order, where we start the right-hand side with del L by del A, combine it with del A by del Z to give del L by del Z, and then again with del Z by del U to give del L by del U. And finally, combine and form del L by del W1, which is the partial derivative of the loss with respect to the parameters which we were after. And for completeness, we can do the same with W2. So this time step 3 estimates del L by del V, and step 4 combines this with del V by del W2 to give us del L by del W2. So now taking the same approach for optimization of cross-entropy loss estimated from logistic regression predictions, on the far side we have our cross-entropy loss, which is a function of f, the sigmoid function, and this in turn is a function of z, which, compressed to fit into the space, is a function of w1, w2 and w0. So the first thing that we need is the derivative of cross-entropy with respect to f, which I'll derive in a couple of slides' time for completeness, but essentially for what follows you just need to know it. And it's given by this. Likewise, the derivative of the sigmoid with respect to z is given here in green. So what remains is to combine these with the partial derivatives of z with respect to w1 or 2 to get the partial derivatives of the loss with respect to the parameters. So here we multiply the derivative from step 1 with the derivative from step 2 and the derivative from step 3, which for w1 is x1. Hopefully then you can see that the f1 minus f terms cancel, leaving a simpler expression of f minus y times x1. As promised, for those who are interested, the derivative of cross-entropy, building together results from the simpler rules that I showed earlier on. Specifically, the derivative of log x is 1 over x, and the derivative of log of 1 minus x using the chain rule is minus 1 times 1 over 1 minus x. Then this tells us that the derivative is, taking the minus sign out of the brackets, y over f from the derivative of log f, then 1 minus y times 1 over 1 minus f from the log 1 minus f term. These can then be rearranged by multiplying back through with the minus, combining everything over a single denominator by taking the denominators 1 minus f up to the left and f up to the right. Again, once these terms are multiplied out, we have a yf and a minus yf term which cancel, returning the expression that we saw on the previous slide. And if you appreciated this and want to know where the derivative of the sigmoid comes from, you can follow this link. On the other hand, if it's all gibberish to you, then it's not essential to know. Finally, a couple of extra points. So far, we've been deriving the loss for a single example, What you will actually need to do is estimate the average loss across all examples. So accordingly, this means that the partial derivative of your full cost can be estimated from the mean of partial derivatives over all examples. And then when implementing these things from scratch in Python, you best use vectorization. So by this, what I mean is use the efficient routines of NumPy, which significantly speed up matrix operations. For example, numpy.mapmul, numpy mean, sum, exp, and log. So in other words, while I've defined these computation graphs in terms of loss with respect to one training example, what you should be doing is writing up your implementation with matrix operations representing x, z, f, y, and l for all examples. So bearing that in mind, how would we convert this function here from a single expression of scalars to a matrix operation? Remembering that matrix multiplication multiplies the elements of rows of the first matrix with columns of the second matrix, and then sums these element-wise operations together to get the element of the output matrix, which here is C. So for example, if we were estimating the element C12 of the multiplication matrix, then we would get this from A11 times B12 plus A12 times B22. So this times this. Or alternatively, if we were looking for the element C33, then it would be A31 times B13 plus A32 times B23. And I got this from the Wikipedia site example of matrix multiplication if you need more examples. Therefore, if x, y, and f have the following shapes, what I'm asking is, how would we implement this as a matrix operation by subtracting y from f and then multiplying the result by x? For the answer, see the quiz linked to this video. So in summary, the output neuron in a neural network for classification can be modelled just as a logistic regression classifier, and indeed the hidden neurons each behave similarly, although as you will come to see in the next lecture, we tend to use different activation functions. During optimization, we are seeking the values of the weights which minimize a cost which reflects model accuracy, but isn't model accuracy because that would be discontinuous and impossible to differentiate at all points. Therefore, instead, we use cross-entropy and make steps in the direction of the negative gradient. This loss is not a direct function of the network weights and therefore needs to be estimated using the chain rule of calculus. Computation graphs are therefore designed to help visualize the chain of operations and help support implementation of forwards and backwards passes. This concept forms the basis of neural network coding languages such as PyTorch, which we will look at later this week, and TensorFlow, where creating graphs of operations becomes increasingly vital as the scale and complexity of the network increases. So that's it for implementation of logistic regression. Please do attempt the Keats quiz, as this will test the core knowledge of the important concepts. And then in Monday's tutorial, please try exercise 1 from the notebook. You should at least be able to implement a forward pass using vectorization, and with help it's hoped that you can implement a backwards pass. At the same time, don't panic if you can't. You won't be assessed on your ability to do it.